So in this video, I just wanted to briefly go over the concepts of the SI units along with engineering notation. And I'm sure that many of you have seen this before, so I'm going to kind of move quickly through this content following the organization as it's presented within your book. So why do we need to worry about actually scaling units using the SI system in both general scientific along with specific engineering applications? And the reason being is that oftentimes the same physical principles are going to be explored, or in our case as engineers, applied at dramatically different scales. So if you think about, for example, taking a specific example of describing the flow of charge, which, as we'll see a little bit later on in this lecture, corresponds to the physical quantity of current. People need to work with that physical phenomenon at dramatically varying scales. They could be designing new nano devices. They could be working on existing consumer electronics for like cell phone applications, or they could be dealing with the distribution of power at long distances. In each case, the underlying physical quantity that they're working with is the flow of charge, which we will see is defined as current, and is measured in the SI unit of amperes. However, rather than define a different measure or a different unit or quantity of current at all those different scales, say I'm going to use this unit to measure big current, like take a physical distance analogy. I'm going to use this quantity to measure miles, and I'm going to use this quantity to measure inches, and this quantity to measure feet, and so on. It's a lot easier to say we're going to use a common base unit, and we'll dig into a little bit what your book is referring to when they refer to base units here in a minute. But a common unit that we either make bigger or smaller using multiples of 10, which can be represented compactly by the idea of a metric prefix. Now, going back to what I was saying a little bit earlier about this concept of base units, so your book presents table 2.1. And in this case, what they're basically saying is that a base unit they're going to define as a subset of units that, if they are defined, from which you can define all new units as some linear combination of those. So it's kind of, for those of you that are familiar with the concepts of linear algebra and basis vectors or basis functions, it's kind of a similar idea as to why they've chosen that name base. So maybe the easiest thing to think about is in Newtonian mechanics. If you look at Newton's second law, F equals ma, if you define the adequate units to measure mass and acceleration, so in this case kilograms, units of distance in meters, and units of time in seconds, then therefore the unit of Newton is actually defined or constrained in terms of those fundamental quantities. So the things on the right can be viewed as base units, and the thing on the left can be viewed as a derived unit. So that's kind of the concept that they're referring to here. So this is, if you look at this and you say, oh, these aren't all the units we need. In fact, in this class, we'll need a volt, we'll need a farad, we'll need a Henry, and so on. The idea is that all of them can be derived from these units, which is why they are referred to as base units. However, it is important to note that oftentimes within the scientific literature, a base unit will just be referred to as a physical SI unit that is not scaled. So for example, a volt, sometimes people will call a base unit, but a millivolt, since we're taking that and we're dividing it into 1,000 pieces, since milli corresponds to 10 to the minus third, that would be referred to as scaling a base unit. So one thing that you're going to have to remember, or just keep handy at least, and we'll talk about which subset are the most important here in a minute, are all the prefixes that correspond to your powers of 10. So for example, we just talked about milli, which is pronounced by its name, abbreviated by the symbol lowercase m, corresponds to a multiple of 10 to the minus third. And multiplying by 10 to the minus third is the same as dividing by 10 to the third, or dividing by 1,000, or cutting the quantity of that unit into 1,000 little pieces. So oftentimes when we work with these scaling prefixes, they can come a bit ambiguous to us, and we kind of lose track of the fact that they're dramatically modifying the underlying size of our units. So how horrible would it be if we necessarily had to memorize? If you notice here, there's a pattern other than the 10 to the minus 1 and 10 to the minus 2, and they're matching positive quantity. Each of the remaining prefixes that are listed in this table are multiples of 3. And that is intentional, and it's related to the idea of engineering notation that we'll talk about in a minute. But before we go any further, let's just look and get some practice of dealing with examples related to metric prefixes. And one thing that I wanted to call to your attention is I actually, on the course website, have added a subfolder under files that is named lecture example scans. So if you go into chapter 2, you'll see each of these that I did for our current notes. So this is the module 1 examples that we're looking at now. So if you go back to that first problem, we were told that a krypton fluoride laser emits at a wavelength of 248 nm. If you don't remember that that's nano, what you would do is look at the symbol here, n, match it to the name nano, and notice that that is a 10 to the minus ninth multiple. We're asked that to say whether or not this is equivalent to which of these underlying quantities. So as we'll see in the next portion of this lecture, 248 nanometers is actually the appropriate way to express that, because nano is as a prefix, 10 to the negative ninth. Negative 9 is a multiple of 3. And this number is between 1 and 1,000. However, it's just kind of getting some practice to see how you would manipulate it. So the way that you would approach this problem is you notice that they may wish to express the same quantity in millimeters, micrometers, or angstroms, which we'll see we don't actually need to worry about in this case. But how would we go about, like, for example, expressing 248 nanometers into millimeters? Well, remember that nano, by definition, is 10 to the minus ninth. And if we want to express in millimeters, we need to factor 10 to the minus ninth in terms of a factor of 10 to the minus 3. Now, why? Because 10 to the minus 3, remember, corresponds to the prefix milli. So I take the 10 to the negative ninth. I know that I need to factor it in terms of a 10 to the minus 3. By your rules of exponentials and common bases, if I have a factor of 10 to the minus 3, to go back to the 10 to the minus ninth, I need a factor of 10 to the minus 6. So take the 10 to the minus 3, make it a milli, and the quantity or the number that remains is 248 times 10 to the negative 6. Now, if you actually wanted to express that not in scientific notation, but in long form, what you would need is to take the decimal, which is implied to be to the right of the 8, and shift it to the left because this is a negative exponent, 3 places. So that will take you all the way back to the front of the 2. That's 3 of those. And you will have to append an additional 3 zeros in order to convert this to millimeters. So if you notice in millimeters, 248 nanometers, which is incredibly small, if you convert it to a larger unit of millimeters, it's going to be an incredibly small number there. So 0.000248. And if you look at that, is not the quantity in millimeters. So if you take a similar approach to convert to micrometers, that is the Greek letter micro, which looks like a U. It's actually the letter, it's the Greek letter mu, which corresponds to micro. There, if we go back to our table, if you don't remember that, you're trying to factor out a factor of 10 to the negative 6 because that corresponds to micro. So to decompose 10 to the negative ninth in terms of 10 to the negative 6 times something, the factor that's remaining is 10 to the minus third. 10 to the minus 6 is just micro. To absorb 10 to the minus third into this number, we'll do 3 decimal shifts to the left. That will take us to 0.248 micrometers, and that as actual answer C. So 2.2, a single logic gate in a prototype integrated circuit is found to be capable of switching from the on to off state in 12 picoseconds. Usually, hopefully everyone has these memorized, but if not, kind of the thing I keep in my head is milli, micro, nano, pico, and I know those are going in multiples of 3 because of what we'll talk about next. So that is 12 times 10 to the 12 picoseconds. That is an incredibly small thing. And what they're asking us to do is convert it to nanoseconds. And if you think about that progression that we just did, milli, micro, nano, a nano is actually a bigger unit than pico. In fact, 1 nanosecond is equal to 1,000 picoseconds. So you might actually look at this right away and see that you might end up to a little bit of issue when you try to do this problem. And let's go through and do it. So if you are converting 12 picoseconds and trying to put it into nanoseconds, remember that a picosecond is by definition 10 to the negative 12. So in order to express that in terms of nano, you would have to factor out a factor of 10 to the negative ninth. And then to get back to pico, or 10 to the negative 12th, 10 to the negative third would be remaining. So if you absorb that 10 to the negative third into the 12, that's going to make it smaller. And you're actually going to get 0.012 actual nanoseconds. And that's not surprising because, again, remember that pico is a smaller unit than nano. So when you convert to nano, it's going to be a smaller number than you originally started with. So actually what you see on this, and I made a little bit of light on it because I've been a bit disappointed with the book so far, is that the correct answer actually isn't included here. So, and once you get a hang of this, you'll see, okay, to go from pico to nano, there's 3 orders of a magnitude difference, and you're going to a bigger unit, so you need to make this number smaller. So shift 3 to the left. Clearly, that right answer is not included. So I made a joke about getting a PhD and writing your own textbook if you want. So in terms of engineering notation, all that's going to be is a particular case of scientific notation where the quantity or the number actually is within the range of 1 to 1,000, inclusive of 1 and not inclusive of 1,000. And what is going to happen is you can kind of think or prove it to yourself. If your quantity is restricted within this range, then your powers of 3 in scientific notation, or powers of 10 rather, in scientific notation, are all going to be multiples of 3. And what that's going to do from a practical point of view is give you less prefixes to memorize. So when we go back to the way that these prefixes were presented in the table, that's why I said that for everything other than -1 and -2, everything beyond that, or on the positive side as well, is a multiple of 3. So let's look at some couple examples here. Here we're given 0.095 W. That is the SI unit for watts or power, which is a joule per second, but we want to convert it to engineering notation. How would we go about and do that? Well, let's look at the actual examples from, I should have known, I think they're actually on the bottom of this file. Sorry about that. There we go. They're divided by modules. So 0.095 watts. To convert it to engineering notation, we note that this number is not between 1 and 1,000. We can make it between 1 and 1,000 by shifting the decimal 3 places to the right. That's basically making the number 1,000 times bigger. We just can't say, oh, 0.095 is equivalent to 95. If we wish to make the number 1,000 times bigger in order to make it between 1 and 1,000, to compensate, we're going to have to multiply by an adjustment factor that's basically going to undo what we did. So when you take 0.095 and you want to make it between 1 and 1,000, note that you would have to shift the decimal 3 places to the right. You can't just do that, though. So when you do that, you have to compensate by multiplying by a factor of 10 to the minus third. So these two things are then equivalent. And 10 to the minus third by prefix is just represented by milli. So 0.095 watts is just going to be 95 milliwatts. And as I mentioned here, always do a sanity check. If you're starting with a quantity that is less than 1, then the order of magnitude, or the power of 10, better be negative, and that corresponds to a prefix, something that could look like milli. So if you did this problem and you forgot that when you compensate for moving 3 places right, you multiply by 10 to the minus third, you would get kilowatts, and you would say, well, clearly, when I convert from something that's less than 1 watt, it would not be in kilowatts in engineering notation. So second problem, 1,244 millivolts. We're asked to convert that to engineering notation. First question is, why isn't it in engineering notation? Well, 1,244 is too big. It's larger than 1,000. Remember, it's up to 1,000, not inclusive. Could we do something about it by simply absorbing the prefix into the number? Well, milli is 10 to the minus third. Correct. And if you absorb 10 to the minus third into this number, it's just going to shift the decimal place 3 places to the left. So that will give you 1.244. That is an acceptable number. It's between 1 and 1,000. So this is an engineering notation, 1,244 millivolts. Since millivolt is a scaled down version of a volt, when you convert it to a volt, the number will get smaller, as it did in that case. So hopefully this was a good review for you, and I will see you in the next video.